Hey everyone, and welcome to This Explainer. Today, we are diving into a truly monumental shift in how intelligent software is being built. I mean, think about it. For a long time now, we've all been completely fascinated by basic AI chatbots, right? You ask a question, and it gives you an answer. It's a neat trick. But what happens when you want an AI to actually do real work for you? Like, what if you needed to book a flight, update a complex project tracker, or conduct deep, multi-step research on a brand new topic? To get there, we absolutely have to move beyond these simple foundational conversational models. We need to start architecting true, enterprise-grade distributed AI workflows. Basically, we are moving out of the era of the chatbot and stepping right into the era of the AI workforce. Let's get into it.
So, this brings us to a fundamental question. What actually happens when one AI agent just isn't enough? For a while in the industry, this concept of the lone wolf agent was super popular. The idea seemed great on paper. If you just build one giant monolithic agent, you entirely avoid the headache of making multiple AI agents talk to each other. But here's the reality. As your workloads scale up, this lone wolf hits some incredibly hard limits. It struggles with complex reasoning over long periods of time, it gets completely confused when you hand it too many tools, and its context window, it just overloads. When you try to make one single agent do absolutely everything, it usually ends up doing nothing particularly well.
All right, so here is our roadmap for exploring the AI workforce today. We're going to start with 1, the single agent limit. Then we'll move into 2, 3 multi-agent architectures, 3, the 4 Cs, 4, agent communication strategies, 5, transforming to agent flows, and finally, 6, handoffs and guardrails. We're going to go step by step to see exactly how this whole ecosystem comes together. Okay, let's jump right into section 1, the single agent limit. We really need to establish exactly why that single monolithic agent eventually hits a brick wall. A single agent loaded up with every tool, every domain, and every set of instructions tends to perform noticeably worse than a specialized team of agents. Why is that? Well, first off, we have complex decision-making limits. A lone agent really struggles to decompose novel problems or reason about complex dependencies when the task is just too broad. Second is context window overload. Think about it. If an agent is trying to do 10 different things at once, its memory fills up with completely irrelevant noise, making it lose track of its core goal. Third, we have tool usage constraints. If you hand one agent 50 different tools, it gets easily confused about which one it's actually supposed to use at any given moment. And finally, the inability to switch focus. A single agent simply cannot parallel process the way a distributed system can. It's just not built for it.
Moving right along to section 2, 3 multi-agent architectures. So how do we actually fix this lone wolf problem? We do it by building an agency, utilizing distinct structural pattern blocks that you can literally mix and match to fit your needs.
Before we look at those specific architectures, we need to clearly separate 2 foundational mechanics of any multi-agent system. First is decision-making. This is the authority to actually commit to the next action based on the available context. Second is communication, meaning what context flows between agents and how does it get there. You constantly have to ask yourself, which agent holds the authority to act right now, and what information do they actually get to see? Giving an agent the precise filtered context it needs matters just as much as giving it the authority to act. Too little context, it decides blindly. Too much context, the signal gets completely lost in the noise.
All right, let's look at 3 well-established patterns for building these multi-agent systems. On the top left, we have the flow pattern. You can think of this exactly like an assembly line. Control and decision-making transfer sequentially, step 1 to step 2 to step 3, toward a single goal. Now, on the bottom left is the orchestrator, or the hub-and-spoke pattern. Imagine a boss managing a team of highly specialized experts. Decision-making is centralized right there at the hub, and specific tasks flow out to the workers. Finally, on the right, we have collaboration. This is your peer-to-peer think tank, where agents actually share control and communicate directly with each other to solve really ambiguous, complex problems. Now, as you might guess, no architecture is perfect. Every pattern trades capability against token cost and latency, and it's absolutely vital to choose the right tool for the job. The flow pattern, it's perfect for well-defined steps because it is super predictable and easy to debug. But it's fragile. If one agent in that assembly line fails, the whole line stops. The orchestrator is highly robust and handles complexity brilliantly, making it great for direct user interaction. However, it requires strong guardrails to keep that main boss agent from hallucinating or going off track. And the collaboration pattern is amazing for ambiguous goals because it generates emergent ideas, almost like a researcher and a critic debating a topic.
But man, it is costly, and it has very high latency because of the massive token usage. Ultimately, the right pattern is usually the cheapest one that reliably meets your specific requirements.
Okay, let's pivot to section 3, the 4 Cs. Let's see how all of this builds into the essential wiring that connects these architectural pillars together.
When you are architecting these complex systems, it really helps to keep a simple mental checklist of the 4 Cs: command, control, communication, and coordination. We've sort of talked about the first 3 already, but that 4th C, coordination, is incredibly important. It's what defines exactly how agents execute along a single path, parallel paths, or multiple branching paths. Like, will your agents use hierarchical coordination, where a strict manager breaks down subtasks, or will they use a peer-to-peer network to organically reach a consensus? These 4 Cs dictate the absolute fundamental behavior of your entire AI workforce. That leads us perfectly into Section 4, Agent Communication Strategies. Honestly, this is arguably the most critical piece to get right, because I promise you, if your agents talk too much, you are going to pay massive financial and computing costs for context bloat. So here's how we can actually manage that communication. Looking at the top flow here, we have message or object passing. In this setup, agents only pass specific required messages from one to the next, entirely restricting intermediary agents from seeing everything in the system. The middle diagram shows shared memory, which is basically a big conversation thread where every single agent reads and writes to the exact same space. Finally, down at the bottom, we have agents connected as tools via the Model Context Protocol, or MCP. This is incredibly powerful because agents pass data to each other the exact same way they would call a standard software function or API.
We really need to talk about the cost versus capability here. Imagine you use a shared memory thread, a downstream worker agent that is reading the full history of an orchestrator, and 3 of its sibling agents is paying for expensive context it absolutely does not need. Every single token of that shared context gets billed on every single LLM call. It adds up fast. Message passing, on the other hand, gives you high efficiency and keeps your agents fiercely focused on their specific tasks. Now, it does require you to write stricter filtering code up front, but it is well worth it for the efficiency gains.
All right, Section 5, Transforming to Agent Flows. Let's take all this theory we've discussed and apply it with a concrete teardown, so we can see exactly how to transform a struggling single agent into a highly efficient multi-agent workflow. Take a good look at this before and after setup. At the top, we have this bloated, generalist single agent. Let's say it's trying to research polar bears. To do that, it has instructions to use web research tools, sequential thinking tools, and local file system tools. It is carrying all that cognitive load at the exact same time. It's too much. But look at the bottom. We've completely transformed it into a crisp 3-part assembly line. First, we have a research tools agent that only knows how to search the web. It does its job and passes its output to a planning agent that only knows how to think sequentially and organize data. And finally, that gets passed to a file system agent that only knows how to write files to the drive.
So the absolutely crucial point here is this: specialized roles mean specialized tools. By tightly scoping those MCP tools to very specific roles within the flow, the whole system scales brilliantly. Each agent encapsulates a well-defined, narrow set of tools, and, this is key, it has zero knowledge of the other agents. This makes the entire workflow significantly more predictable and deterministic. If your final document doesn't write properly, you know exactly which agent failed, the file system agent, and you don't have to debug a massive 1,000-line monolithic prompt to fix it.
Which brings us to our final execution phase, Section 6, Handoffs and Guardrails. How do we safely pass the baton between all these specialized agents without losing control in a live production environment?
Let's break down these 3 flow strategies step by step. Over on the far left, we have a basic conversational flow. This is noisy. Every single tool call, every random thought is just dumped into one massive thread. In the middle, we have the pass-off flow, where agent-to-agent communication is tightly controlled through your code, filtering only what the next agent actually needs to see. But look at the right side. Conversational flow with handoffs and guardrails. This right here is the gold standard. In this setup, guardrails actively validate the input and output data between the agents. So, if your research agent suddenly spits out hallucinated data, the guardrail catches it instantly and short-circuits the flow before the planning agent even sees it. It literally prevents catastrophic cascading failures across your workforce.
I love this quote because it perfectly captures the main takeaway of all this. Moving to real enterprise AI isn't just about relying on raw underlying model intelligence anymore. It is deeply about engineering scalable, recoverable, and observable pipelines.
By blending typed inputs and outputs, placing those deterministic checkpoints between your specialized agents, and enforcing strict guardrails at every handoff, you graduate your AI from being just a neat tech demo into a highly dependable, production-ready system.
As we wrap up, I want to leave you with this somewhat provocative thought. When you look at your own AI architecture today, are your agents just running simple tools in isolation, or have you actually architected them to collaborate, delegate, and communicate as a true, scalable AI workforce? The leap from a single simple chatbot to a robust agentic assembly line is absolutely transformative, and now you have the foundational blueprint to start building it. Thank you so much for joining me on this explainer, and honestly, I can't wait to see the incredible multi-agent systems you all are going to build. See you next time.